So there are three approaches: thermochemical, biochemical, and hybrid approach. Thermochemical, temperature, pressure, catalyst. You need to know some reaction engineering concept, how reactions happen. So if you put in that, this is thermochemical approach. Using thermochemical, you can simplest thing you can burn, get heat, and heat can give you electricity. The next option you have is you can gasify partially biomass. You can gasify. If you want to gasify, you don't want to do combustion. That's easy. You supply excess air, you can burn. But you don't want to do combustion. So we need to cut down oxygen, such that all carbon does not go to carbon dioxide. You want to gasify but don't want to lose energy value. You supply limited amount of oxygen. That is called gasification. I will tell you why you want to do that. Then pyrolysis. You don't want to go to that high temperature in gas phase. You really want to make liquid out of it. Gas will have, no matter which process you do, you will get solid, liquid and gas also. Then combustion you get solid, which is gas or some carbon dioxide. Gasification you will get all three. Some tarry material you will get, some char you will get. Pyrolysis again you will get all three. But you want to get oil more here or char more here. So this is typically done thermochemically. This side I have been working for my group and many others are working. It's called hydrothermal. Only because this side requires dry feedstock and drying cost energy. So can we use reaction engineering or water chemistry to see water can do reactions here as a solvent and so that part is called hydrothermal. And then we have to look at water at high temperature and pressure. So there are two different phases, subcritical and supercritical. I will come back on that. But using these things again you can make all these products. So thermochemical conversion, cold and for hydrothermal, which is very similar. So let's look at the journey. We are looking at a scale. Pyrolysis is no air or no oxygen. Gasification is little bit oxygen and combustion is excess oxygen. Okay. How will we put in number? So that is called equivalence ratio. We call it PR. PR is 0. Equivalence ratio is 0. For gasification, equivalence ratio is 0.2 to 0.4, ideally 0.2 to 5 or something like that. For combustion, you want to supply enough oxygen, you make sure everything burns, so you can access oxygen to greater than 1. Okay. So, equivalence ratio is how much oxygen you needed for complete combustion versus how much you supply. That's equivalence ratio. So these are the ways to present number and start working in processes, control area. If you can plot it, equivalence ratio of gasification here, pyrolysis is here, you will see it's a lower temperature than gasification, and combustion is high temperature and excess oxygen. Thermochemical, you have different reactors because you have high temperature materials, so fixed bed reactor, fluid bed reactor, auger reactor, plasma. Pyrolysis, we'll talk about this. So look at video when you have time, it's very clear. But what is pyrolysis? Not burning. Burning is combustion. Carbonize, right? But eating something in absence of air is pyrolysis. Pyrolysis will be no there is oxygen in biomass. That will try to come out and burst out because you saw the formula, 30-40% oxygen. That will take some carbon with it, some hydrogen with it, right? Oxygen does not come out alone. It is oxidized from CO2 or water. So it will take some CO2, so when you do pyrolysis, even if you didn't supply oxygen, you will see some CO2 coming out because of inbuilt oxygen. You will see some water coming out because the biomass had it. And then we got the gas phase, some oil will form and some carbon will be left in form of carbon. How oil will form? Solid I can imagine, take that, decarbonize. Gas I told you will come out. How oil will form? Because pyrolysis we do for oil, pyrolysis oil. So how oil forms? Anyone? So what happens when you heat something? So now I gave you enough background, biomass, water content, cellulose, hemicellulose, lignin. These are all polymers. Okay? And then I put you to an ultimate and approximate analysis, 2 elemental. Now you think when you are heating, what happens to cellulose, hemicellulose, lignin? They are polymers. If we heat polymer, what happens? They will break, right? They will break, melt, all those things will happen. So when they break, depends on how much heat you are doing. Right? Faster the heating rate, higher the temperature, they will break more. Okay? Now, gas formation is then it's broken completely. You cannot combine back. It's a permanent gas. Right? Methane, CO2, water and all, paper, they are permanent gas. They stay like that. But if you have a bigger molecule, which is still not gas, cannot expire. Basically it's a reactive species. Broken down because of temperature, it is still reactive, it's not gone to gas phase. When you cool it down, what will happen? You try to go back. There are so many reactive species inside this glass and they are trying to either go gas or liquid and gas or solid, but in the end they will start joining because of chemistry or radical and so when they join together, when you cool it, they drop, it becomes time or oil. Right? So that's how you get oil formation. So it depends on temperature and heating rate. So you get oil also. Now you got a system here, you can produce oil, you can produce gas, and you can produce charcoal. What we need to produce, we need to. This is a municipal solid waste and we are happy with some char and put in ground and lawn, we need more char. This is a fuel industry and we want to make diesel or gasoline. We need to tune such that we get more oil. Okay. Gas has so much nowhere to go because it's low temperature. You go higher temperature than you go temperature. Okay, so that's what is pyrolysis. This is the last slide. So fast pyrolysis, tuning, I said that. If you are trying to make oil, you want to do fast pyrolysis. It will give you up to 60 to 70% of oil. Because it keeps so fast heating. Imagine 200 degrees Celsius in 10 seconds. 400 degrees in the pyrolysis temperature, typical 400, 500. You can heat in 10 seconds. And it breaks down so fast, then cools so fast, get more oil. Okay, so if you are looking at for fuel, liquid fuel, do fast pyrolysis. Typical time is 10 seconds, 2 seconds, 5 seconds, 6 seconds. And then you will have some gas, some char. So you see less char. If you are trying to balance both, do the heating rate, it is slower but not very slow. You will get more You are trying to do in between, flow completely, then in between medium is not given here. But if you are trying to go slow just for charge, you go to slow pyrolysis. The carbonized movement will make more charge. And I said gasification also you will get some charge and other things, but gasification is done for making gases. Okay, so you will see 25% gases, less charge and oil. I will stop here, wastage rate, and I will come. From last session, we have started discussing thermochemical and biochemical conversion. Hello? Yeah. So any questions? So let me go off topic a bit, and then I will say if you are looking for higher study and if you are looking for masters, requirements are different than if you are looking for PhD. Okay. Masters, many people go self-funded also. Okay. And I will tell you the reality. It's very difficult to get funded masters in US. You will get it, many people get it. One of my students got it, but many of my students didn't get it. So if you are looking for masters and funded masters, you have to be selective how to go for that. If you are looking for PhD, many universities have two kind of PhD. One, you can go direct PhD just from BS to PhD. Okay. Some university ask for masters then PhD. Okay, so that's the two different routes you can take. So when you are applying, you have to look at the guidelines, what kind of offer they do, and never be shy of emailing graduate program director of that department. Okay, that's the best resource you have. Whoever is there, they will respond to you. Okay, so look at the website, look at graduate program director name, and write to that profession. So that will be very helpful, and they can say that whether TA, there are two kinds of funding you can get. One is RA, research assistantship, is called GRA, graduate research assistantship. The other one is called GTA, graduate teaching assistantship. So teaching assistantship is something paid by department. So let's say I'm teaching a course and I have 50 students. So it's very difficult to do all grading and homework for me for 50 students. So to support, department hires TA, teaching assistants, and they are paid equally like RA. Okay. So if department has TA need, they will take. If they don't have TA need, then you have to depend on RA if you have RA need. So that's one option you should be looking at, GPA or GRA option. So master, many of the students I've seen, they go self-funded. It depends on what's the background, how much you can afford. But they go self-funded, but they find options when they are in campus. Okay, sometimes they get the library, some other department, and they help on those things. So that's also a possibility. But that's also a risk, how much you want to take that. Okay, most of the time they get it. Okay, but something to think about. For PhD, self-funded, I would say not a good option. You won't survive that much dollars. Expensive. Okay. So if you get a PhD, basically you want to be funded, and when you get funded, PhD fees are paid. Okay, so you don't pay any fee. In master, even if you are funded, many universities they will ask you to pay in-state tuition or 1/3 of it. So your stipend and tuition becomes neck to neck, so you don't have much margin. So going for just master is a little costly option. Depends on background. Some families can take that. Some families is difficult. Some students cannot. Difficult. But PhD, if you look accordingly. So do TOEFL or IELTS English test. It must. That's the discussion starting point. Look for application method and other things, RECO, and start interacting with graduate program director. Other thing you want to look at is what kind of university you want to go.
There are 4,000 or more universities there. Okay. So location also becomes important. Some part of US is very good, nice. You like very similar to here where I live. Weather is very similar to here. And we have all four seasons. Some part of US is very different. 6 months cold, very cold. Some parts is very hot. Okay, so you need to look at it where you want to be. Okay, and that's also a good criteria. Once you go and then you will start seeing it's a surprise. Okay, so when you choose university, give attention to that. There are many good universities in Midwest, Mid-East and other things, but there are not many big cities around, many not big industry around. So those kind of things matter. So be choosy on university selection also, which state you want to go, West Coast, East Coast, Texas, also New Jersey, all those things matters. Okay, and again definitely if you are reading, emailing, be careful on emailing, be specific, don't overload with information too much. Many a time people read on phone nowadays, right? Some email are quickly, so if it is overloaded, you will get to go to the computer and then it will go. So start a simple discussion and then build on that. Okay. I hope it's helpful, and then let's come back to what we have been discussing. Conversion technology, as we were talking about, that it will be one of the paradoxes. We are talking is very complex. It's not straightforward. It's a mixture of aromatic compounds, sugar, carbohydrates, protein compounds, nitrogen, sulfur, carbon, many things are there. And again, I said that this is cellulose, this is hemicellulose, this is lignin, all mixed together. If you want to make ethanol biochemically, you are looking at this and this, you cannot ferment this, right? So what we do with this, how we separate, all these things matters in biochemical. So thermochemical conversion processes, I was talking conversion, gasification, pyrolysis, liquefaction and hydrolysis, right? So let's say pyrolysis we talked about, you have a different heat temperature and you will get all three, and how to tune it, you will get oil and other things. So we'll come back on that. But if you want to do biochemical, you want to utilize sugars or alcohol, am I right? And we are not talking starch, we are talking cellulose now. So how will you reach to sugar here, carbs, when lignin is protecting? How will you reach there? Any thoughts? You design some enzyme which will break down cellulose. Okay? It will do fantastic. You know that enzyme is good. But how will you subject to that? How will you make sure enzyme reaches to cellulosic sites? What idea you have? Let's say you got sawdust, wood dust, and you want to do enzymatic hydrolysis. So how will you make enzymes accessible to cellulosic sites? What we need to do? If you put as it is, sawdust and enzyme and your medium and all, will it work? Will it work? No, because lignin is a barrier and it's not going to allow you to reach there. So you have to deconstruct it, you have to treat it, you have to break it down, somehow do that. The paper industry does all. So something that's called pre-treatment. And pre-treatment is exposing sugar, increasing surface area that enzymes can see that they can do that. So now doing this is a cost center, right? You are going to add cost in using pre-treatment process. Pre-treatment can be chemical, physical, or you can just grind it and all, a combination of those also. And once you bring that, then you have sugar, so you can do fermentation and also. So if you compare biochemical versus chemical, thermochemical processes, we already talked what the game you have. One is low temperature, another is high temperature. Okay. One is microbial process, another is thermochemical catalytic process. Okay. So both are using catalyst. Right? Thermochemistry, if you are doing, you are using catalyst here. You expedite the reactions and save the temperature. In biochemical also you are using enzyme as a catalyst, a biocatalyst. You need catalyst understanding how they work, how they reach to sites, how efficient they are. Time-wise you are dealing with different timeline. One is hours, days, another is seconds, minutes. Efficiency-wise, that is moderate. This is better efficient because it's faster. But purity-wise, you might get purer compound here because you are not disturbing too much, so not breaking everything. End products, biogas, ethanol, butanol, everything. We talked about, just summarizing, for biochemical composition analysis is important. How much? That's how you will know that how much carb can go to sugar and other things. And thermochemical proximate analysis, ultimate analysis are more important. Then definitely physical characteristics like how easily you can grind, pelletize, heating value and other things. Anaerobic digestion, right? We know very well, most of you know very well. What happens here? There are two kinds of setup, aerobic or anaerobic. Okay. If you have organic matter and aerobic condition, what product we are going to get? CO and water, aerobic outside, right? That's a stable product, it's fully oxidized product. If you are doing anaerobically, you have microbes, but you are going to get methane and CO2 itself. Okay? And some unstable products, and some sulfurs. These are pretty basic, I'm just moving out. What are the aerobic decomposition, anaerobic decomposition? You all know more. Are you familiar with this growth curve? Alright, cell growth, so lag phase and exponential growth phase and all. Fermentation we talked about. How we do that? So sucrose, we have glucose plus fructose, so sugar cane juice and all, but fermentation we talked. Okay, so here's the thing. What enzyme is used for cellulosic material? not a starch. So typically it's called cellulose. Okay? And it's a mixture, it's a cocktail. And then for MI, you need another cocktail, hemicellulose. So enzyme cost becomes efficient. So to save enzyme cost, what option you have? So there are two things. One is pre-treatment, second step is enzymatic hydrolysis. Are they independent? Are they independent or they depend on each other? If you do very good pre-treatment, enzymes will be more effective. Effective means faster, less enzyme, right? So you save cost. But for doing very good pre-treatment, you are putting energy, chemicals, because pre-treatment can be chemical pre-treatment, steam pre-treatment, or grinding. If you don't do very good pre-treatment, then you need more enzyme to do that. So they are not independent. Okay, you need to balance how much we want to do. And that's together makes big component of the cost. So you have enzyme cost and pre-treatment cost. If you join together, 40% of the cost, operating cost goes in that. Through our research contribution, can we start reducing that? Okay? That will be more important. It's a cocktail of enzymes, so you have to ferment all sugars. Otherwise, you are losing. Already you have, how much sugar you have in cellulosic biomass? MI and cellulose together, 65, 60, 70% together, right? So you are already 30% less some other material. Out of that, 60, 65%, these are all mixture of sugar. If you don't ferment, our efficiency will go further down. We will losing that. It's all material balance. And fermenting all kind of sugar is tough on enzymes, means how good efficiency. So that's a challenge. If we do pre-treatment, like alkali treatment or acidic treatment, we end up generating some byproducts which might be toxic to enzymes, to slow down. That's another challenge. So resistant to toxic material from pre-treatment, like you might end up selling glucose derivatives in HMF. Okay, glucose will break down to HMS, HMS becomes inhibitory. Xylose will break down to furfural and furfural becomes inhibitory. So you need to minimize this toxic material during pre-treatment. Robust and able to compete contaminant microorganisms. So you need thermotolerant, ethanol tolerant, that's another in fermentation, product inhibition, pH tolerant, high fermentation rate, minimum metabolic other products. So these are the challenges makes tough in biochemical. There are different approaches for fermentation, especially in ethanol. Separate hydrolysis and fermentation. So we have a enzymatic hydrolysis and then fermentation. You can have simultaneous saccharification and fermentation in one. Okay? You can have a simultaneous saccharification and co-fermentation. 5 sugar and 6 go together. Or consolidated by processing one chamber and do everything. So these are the different options you have. Technical barrier which industry is facing, especially when we are looking at corner store, grass, rice husk, and other thing. Feedstock variation and delivery. Analytical method which I have been talking. So all becomes tough. Supply system which we don't see. That's another logistic issue. Soil sustainability. If we dedicated crop we grow, how sustainable it would be. Biomass recalcitrants to conversion. Recalcitrants means difficult to reach to the site, it does not want to change. For that we break down using chemicals, and that's pre-treatment. hydrolysis and fermentation, how easily we can do. Process integration. So what are the different things we are handling in this plant? Solid, which is biomass, and I told you this solid is different than coal. It's fluffy, bulky, it makes bridges, it flies, right? Coal is different solid, which is high density, close well. So that's a challenge, solid. Solid liquid separation. If you put water and biomass, what happens? Does it mix well? Immediately dating problem, it does not date well, and then you have to do that. That's all problem. Process chemistry is very, very complex, especially lignin. I don't know how many of you who have studied lignin. Lignin chemistry is well known for being complex because you saw the structure. 3 monomers, aromatics join in many different ways, many different, so it becomes very difficult. So carbohydrates, if you will heat it, it will decompose by 575 degrees Celsius, so all will be gone, volatile. All those things. Lignin decomposition starts from 150 degree, continues till different temperature. So it has a kind of consistent weight loss. You cannot say, but carbon you know at what temperature it will go in TGA. So it's a very different. So lignin chemistry makes it more complex. So process chemistry. So now I'm bringing, again I say corn, starch, potato, wheat, cereal are easy to ferment. You will see a lot of ethanol industry doing that, sugar can doing that. But we are talking this kind of things. Okay, and I'm showing you how this is different than starch. So corn process or sugar cane process. Let's say if you have a sugar cane juice, what the process will look like if you want to make ethanol. You get sugar cane juice, ferment it because it's almost ready, sucrose or glucose. Okay, ferment, distill, dry ethanol. Let's say you have a starch, corn sugar or something. If you have a starch, then a starch you need to cook, make it softer, bring in solution, basically hydrolyze. This is again commercially known, so this is easy to do, but you added one step, cooking of a starch. And then remaining process remains same. The enzyme is alpha amylase and glucoamylase enzymes. Okay. Now, if you are adding cellulosic process, grass, that's why I am showing the wood. What you added here is started from cellulose. You need to reach these things to get cellulose. Okay? So you need to do pre-treatment. Alright? So pre-treatment you can do thermochemical process, use alkali or acid or something like that. So when you do that, you get cellulose, you do hydrolysis, and then you take the same route. But you generated another product which is lignin, and that needs coal heat recovery. So this is extra, and we want to get ethanol at the same price at corn or sugar cane. So we depend on all of us how good we can do this, so save the cost and match the price. Okay, so these are the challenges, good to take on. Here the enzymes are different, it's costly. Pre-treatment has multiple options. Pre-treatment depends on enzymatic hydrolysis method, which one you take. So what pre-treatment does? It breaks down, somehow you expose it. The fibers are hidden, now you expose it, broke it down. By temperature or by grinding or by chemicals or whatever way. So the only objective of pre-treatment was enhance the rate of hydrolysis or enzymes efficiency and the yield of sugar, because sugar will go for fermentation. So pre-treatment can be physical, physiochemical or chemical. If you grind well, enough grinding will increase surface area, am I right? Surface area means it's exposed more. You can do that, but this is power intensive. Right? Grinding is, see that we run grinders at home, is kind of fun. We quickly switch it off, it's taking too much electricity, am I right? So it's like that. Can be a reason. Physiochemical can do a steam explosion. So exposed to steam and it will open up vesicle stress and do that. Sulfur or CO2, ammonia fiber explosion, supercritical CO2, these are the tested one. In chemical, which we know more, know how to do chemical treatments. So you can use acid, alkali, organic solvents, ionic liquid, hydrothermal, which I was talking. In general, alkaline reagents have high selectivity for reaction with lignin over carbohydrates. If you are using alkali, it's like pulping process, paper making process. They use a lot of alkali. So it breaks down lignin, it goes in black liquor, and you get the thermal fiber, cellulosic fiber. Acidic will hydrolyze hemicellulose. Okay, so you see hemicellulose, it will hydrolyze and it will open up. So this is takeaway message. Higher pH, what will happen? Dilute acid will remove hemicellulose. So we should know if we are using acid, what's going to happen. You expect more hemicellulose in the solution, and you don't want to lose sugar, but it is in solution, so you have to take this and other side also. Control pH hot water treatment we do. Add pH constant or buffer. You can do pre-treatment here also, but it will remove part of lignin, part of iodine. This is calcium balance. You can go fully alkaline, and it will remove most of lignin. So these are the methods you can do. So pre-treatment, I already talked it, but cellulose accessibility, that's what we need. Low capital cost and low pressure system we want, alright? Low energy cost, low degradation. There is another way, microbial fuel cell when you are working, so you can do that. Torrefaction. What is torrefaction? Have you heard about this name, torrefaction? So if you do pyrolysis, you can change into oil, char and oil. And let's say your biomass is 100 kilometers away, and you want to bring it to the pyrolysis plant. And what option we have? We talked yesterday that if you transport as it is, it will be more water, dust and other things. It's bulky material. So one of the way is called pre-treatment, torrefy it a bit. Again, it's energy, heating value, how much you are bringing. If you torrefy and pelletize, it will have more energy given unit volume. Okay? So torrefaction is roasting of biomass. It's like a coffee roasting we do. So basically roasting of biomass. Basically pyrolysis at very low temperature, 200 or something. So what it does, if you roast biomass at 200 or so, what will happen? Some volatiles will come out, alright? And it will clear pores also when it comes out. So volatile bonds, it becomes fluffy, more porous. Now you can compact it, make pellet nicely. So energy density will be higher. I think I am missing some slides. Just give me a moment. depends on different composition, temperature, pressure, vapor residence time, particle size and heating rate. Okay, so now if you are looking at bio oil or pyrolysis oil, you will get bio oil which has a moisture content of 15 to 30%. What is the heating value here? 16 to 19. If we compare heavy fuel is 40. So we pyrolyze something to make oil, right? We expected to have heating value closer to oil. Take any pyrolysis oil, you will get 20, 16 and all. Why we should do this? Turn to liquid, there is no way close to what we want. So why we do that? What benefit we get doing pyrolysis if we are making oil? Anyone? To do pyrolysis, we want to produce oil and the oil quality is still inferior. Quality is directly linked to heating value, which is still biomass. What is the heating value? 15, 16, 17. And oil we get is almost similar. So what we did, why we do? Yeah, so that's fine, but take a drum, okay, and put biomass. Biomass, you know, is 15, 16 megajoule per kg, but one drum of biomass, how much energy will it have? Let's say in a drum we have 40 kg. So how much energy will it carry in a drum? Now, same drum, take this pyrolysis oil and put how much oil you can fill it. Much more energy than this. So even though heating value was energy density per unit volume increase, per unit mass is same. So you can confuse. But now you need to say that we wanted to turn solid to liquid, which is easier to handle, easier to store, and then you can easier to do upgradation. Upgradation means from here to here we can do now. It's a liquid reaction, liquid gas, something like that. It's not solid. Okay? And remember, biomass is hydrogen deficient. So this is hydrogen deficient still. You need hydrogen, add hydrogen is here. But now you can conduct hydrogenation process to upgrade. So that's why we make pyrolysis oil is one of the options. It's an intermediate process, turn into liquid and then you produce. So biomass, we did pyrolysis, you get oil. Now this is a stabilization and upgrading which I am talking. If you are doing fast pyrolysis, the products are unstable. Hold it out, but if you store too much, it will change. So you need to stabilize, you need to remove water, separate the water there, and then upgrade, or you just burn it, electricity or upgrade. The concept what we are talking that economy of a scale. We can think of a centralized facility, and in this facility we are bringing biomass stuff. But if you are bringing oil from here to here centralized, and then you upgrade it, then you get it, right? So we can think of a mobile pyrolysis unit. We have a pyrolysis unit built on a truck or of that size, goes to a forest or wherever, take biochar, make oil and char, and then it brings to the centralized facility and they do reactions like refineries, decarbonization. So that concept might be more suitable than bringing solid as it is. So fast pyrolysis has advantages. Atmospheric pressure, modest temperature, most of the pyrolysis are done at 450, 500 in that range. Disadvantage, high oxygen still I talked. Oil has low heating value, that means low pH it becomes acidic. Crude oil is not acidic. Water content, phase separation is not stable. Different kind of pyrolyzer you can use. Okay. So fluidize, circulating fluidize, rotating, ablative, vacuum, different kind of reactor you can make. How many of you know fluidization? Fluidize. Fluidize. Circulating fluidized reactor. What is fluidization? Just now. So think of wood, a drum load of wood, and say that this is pyrolyzer. So you start heating. This heat will be uniform inside the drum. Will it be? Let's say this is pyrolyzer. Fill the drum. Now you are heating outside. This can be this big or much bigger, right? You see the industrial scale, it's not large scale. So now you have a lot of wood in diameter and you are heating outside. With that it will be effective, uniformly distributed. It will take time, right? The surface will be heating faster, then there will be gradient. To become uniform it will take time. By that time property will change. It's a heat transfer problem. Alright, so how you transfer heat? We know things if you mix well you can improve it. It's nice heat distribution. Mixing that mass transfer and heat transfer both things. Right? And here if you are putting this, there is no way to mix wood chips. You can tumble it, right? But you cannot put a stirrer and mix it. What option we have? So again, whole industry is called fluidization. So you put sawdust, dust here in this, and pass nitrogen or any gas. In pyrolysis, you don't want to pass oxygen or air. Because pyrolysis is done in absence of gas. You pass inert gas, and you have filled with dust, wood, sawdust, very fine biomass. From bottom you pass, what will happen? Just try to rise, right? If too much velocity, it will come out, it is open. And if there is right velocity, it will look like boiling, right? Just like that. Don't go up and it cannot be settled. That's the right time is called fluidization. Made like a fluid like here. Okay? Not exactly liquid, not exactly gas, it's only this fluid kind of thing. It's nice mixing and all. So that's how you do pyrolysis is fluidized. Whole industry does. They know how to do that. So these reactors are bubbling fluidizer, it's bubbling and it comes down, or circulating fluidizer. So you can circulate. So there are different designs, but my point is it's not easier to heat. Easy to heat by one just like that. You need some mixing. So it's done through fluidization. And you need these are the barrier, dry, high oil content, improving oil, we talked about that. Oil you produce is low heating value, high oxygen content, I talked about this. So how you make liquid fuel? Let's say you want to make diesel. You got bio oil, now you want to make diesel. How will you do that? So you get bio oil here. This is pyrolyzer, or whatever, you get bio oil, they separate, some lignin will come out, and then you add hydrogen. So hydrogenation process, remember biomass is hydrogen deficient. At certain stage you have to have CH2, SUH, H2. So that's how you put hydrogen catalyst and temperature 200, 300 range, and you will get oil which can be distilled and plastic. So that's why hydrocracking of bio oil. You can gasify and then run Fischer-Tropsch reaction, catalytic reaction, you can do that. So that's what why we make pyrolysis for bio oil liquid. You have to make bio oil first and then do hydrogenation. And through pyrolysis you can make diesel, and it has been shown. The challenge is cost, how efficiently can
Combustion I already talked. You can have a direct combustion or you can have a co-firing. And last lecture I was talking about what the challenge of co-firing. Right? It does not mix well. So if you have a boiler, you are doing direct co-firing, boiler need to be changed. Right? So you cannot have a single life, you can have two entry separate. You cannot mix because it don't mix well with biomass. Or indirect you have separate. Or you can have parallel with biomass. Advantages of co-firing. Coal has a lot of sulfur, biomass exposure. Power plants struggle how to keep sulfur down. You can mix biomass, it will bring sulfur down. Right? Coal versus biomass I talked. Let's do it. Gasification. So pyrolysis you have a good understanding now. If you are looking for bio-oil, you can make it. Okay. If you want to make charge, just heat at low temperature and you can do it. Gasification, what it does. The biomass can gasify at 700, 800, 900 degrees Celsius, supply limited amount of oxygen, and the mixture will come out is called syngas, which is a carbon monoxide and hydrogen. And this gas has high potential for making different chemicals. You can run gas turbine also, it has energy, electricity, or you can do Fischer-Tropsch reaction. And one carbon and hydrogen. What is oil? CH2CH. Okay? So Fischer-Tropsch came to the solution that you can build the chain, carbon, hydrogen, and so on. Okay? So you can do Fischer-Tropsch reaction, you can get Fischer. Water gas jet reaction, you can make hydrogen, methanol. So all these chemicals you can make from syngas, and if you do biomass gasification, you get syngas, and then you can turn. So that's the advantage of gasification. And there are different types of gasifier. You can repeat technical barrier in gasification. When you do gasification, what happens? Tar. So as part of pyrolysis oil, you are looking for bio-oil. Now you are going higher temperature, you want gas, there will be some carbon. Now it's unwanted. In pyrolysis it was wanted, now it is unwanted. That's a challenge. Ash melting. We are talking 800, 900 degrees Celsius. So ash, which is sodium, potassium, silica, they will fuse together. And in gasifier they will get clinkers and other thing, and they will destroy. Low heating value of gas. We just talk. Gas cleaning is needed because tar will come and many other things comes. So this is Fischer-Tropsch reaction. One you got carbon monoxide and hydrogen. You run at temperature and catalyst, and it forms alkanes. Okay. So this is how you can make a decision from German scientists, and they develop when we are looking for coal to liquid and through how to make. The compound which is called fatty acid methyl ester, is basically biodiesel. So let's say you have vegetable oil, put in an engine, can you run it? Oil will burn or not? What? Alright. But it is, if you have diesel and oil, if you compare, which flows better? Viscosity is higher in case of oil. Alright? Get turned into biodiesel, viscosity is less. That's the challenge to soot formation and other things is not that. So that viscosity, how you remove it, make it biodiesel. So these are fatty acids in. You do trans-esterification, like this side. So 3 fatty acid and this glycerin back both, this is giving you viscosity. Okay. then we cut it off. Then it becomes a straight chain and it's no viscosity, a very low viscosity. Then it's fine. So this is what is done with the alcohol, ethanol and catalyst potassium hydroxide, and to make biodiesel it is very easy to make. You can do it very easily, low temperature, ethanol and sodium hydroxide fatty with ethyl ester, and you get viscol. Viscol is a byproduct of this. Okay. Now this is giving you another product. How can you develop for this one? This is not very clean glycerin because you have ethanol and contaminated. But this is another product. So you can make hydrogen out of it or use in soap and many other things. Okay. Again, material balance, how much you get. Now coming to this is what I wanted. So you have oil and methanol, you get glycerol and biodiesel. And this is blend fuel. Alright? Blend fuel means you have to mix with the diesel. We are looking for drop-in fuel. This one is solving some problem, not entirely. We are looking for drop-in fuel. So can we take this, turn into diesel? Let's call it renewable diesel or green diesel, not biodiesel. Yes, we can do that. Remember, the hydrogen differentiate. So put hydrogen at least 300 degrees Celsius, around that. And you can turn it like a diesel straight. That is called renewable diesel. There are many companies, UOP, one well-known company that take a lot of green.
Is that straight hydrocarbons?
Yeah, these are diesel basically. R1 means long chain, H2, H3. This is end, so H3 and the chain is usually 2. So now this is your drop-in. This is being done. UOP, one company, there are few in Europe. They are taking all kind of chicken paste and rosary and what we call the lean and.
Sir, which food should be better? For example, if we go for pyrolysis and getting oil, and then we are converting this oil to hydrogen. And similarly, we are going here to use biodiesel, and then again.
So your feedstock is too different. Pharmacists are taking
Yes, I understood.
biomass.
Yes, both. Consider both of them are biomass.
Yeah.
Once we go for pyrolysis, getting oil, and then we are converting into hydrogen. Another case, we are going for biodiesel, and then again going for this catalyst and go for this.
No, so that's what I'm saying. We are mixing. What we are talking, if you have biomass, then we can compare between pyrolysis and gasification. Okay? But if you have oil already, vegetable oil, so grease, used oil, waste cooking oil, then fats, chicken fats, what of fats we get, we throw it. Those are oily, those are fatty acid kind of thing. They are like this. These are oil, not cellulose or fibers. So these are used for making biodiesel. But what I'm saying, those are blend fuel. World is looking for drop-in fuel. So those things can be done commercially by adding hydrogen, catalyst and 200, 300 ppb is a proprietary for different company. They are doing that's hydrofining process. They call it. They have their own name. Basic chemistry is adding hydrogen, catalyst and temperature, and you can make a straight chain. And that is the renewable diesel. This is tested and it is done. Okay. So now another topic will come. Let's see. We covered biochemical quickly, fermentation and enzyme. We covered pyrolysis. We covered gasification quickly. We covered biodiesel and renewable diesel. Each one can take hours. Maybe days to go deeper, but this is the fundamental level. Another one process is called hydrothermal process. Remember remember thermochemical, biochemical, and I put hydrothermal. Hydrothermal is basically thermochemical, but it is done in presence of water. So water was not wanted for pyrolysis gasification. Here water becomes a part of solvent and chemistry. You don't have to try. So hydrothermal process, you can do hydrothermal liquefaction. You take water as it is and directly put in a pressure cooker, kind of a closed vessel, and heat it, it will liquefy. And you can turn into food. So then you can separate water and food. So hydrothermal what comes from sub and supercritical water. Okay, combined we call hydrothermal. Hydro from water and thermal state. So what is critical point? Subcritical, supercritical. So critical point of water is 374 degrees Celsius. Okay. At that temperature, there is no difference between liquid and gas phase. They are very mixed phase. Okay, beyond critical point. This phase is called supercritical phase. Okay. Below this liquid or gaseous phase, we have separation. Critical phase, no matter how much you can do, you cannot liquefy. It's a single phase. Okay. So if we are working below the critical point, it's called subcritical water. That means below 374 degrees Celsius under pressure. It's called subcritical. Above 374 under pressure is called supercritical. Okay. Boiling point is here, critical point is here. Critical point. So imagine you have water in a container and it's not copper. You heat it, what happens? The steam gone. Put a copper and keep heating. What will happen?
Steam will also create pressure.
Yeah, pressure cooker basically. Alright? Keep pressure. Pressure cooker is still a low pressure. You can keep building thicker pressure. So what will happen? Vapor beginning, but they are condensing back. So you have mostly liquid phase. Think of water at 200 degrees Celsius and still liquid. Can you imagine? If you don't pressurize, it is the steam or vapor. But if you pressurize, it will be more liquid phase. Okay? So liquid phase reactions, in reaction engineering, liquid phase reaction you can do here for that. So subcritical water, you will see more of the water phase you are doing reactions. If you go above 374, now water is a very well mixed homogeneous mixture where you have vapor and liquid phase, not pressure. No matter how much pressure you do, you cannot liquefy enough this above 374. So these things are wonder for chemical reactions. We have some salt I put here, cold water, salt. What happens to salt? Put salt here in water, what will happen? It dissolves, alright? Put some dust or biomass, cold water, what will happen? It will take time to get wet and other things, alright? In subcritical phase or supercritical phase, put salt here and here, it will precipitate, don't dissolve. That's a point. But if you put some oil, put oil here, it will float, here it will be very rich. Okay, it becomes better solvent. So, this is dielectric constant of water. Dielectric constant to simplify gives you solvent property. Okay, lower dielectric constant versus higher dielectric constant. Lower is more non-polar, higher is more polar. So if you do hydrothermal process, submersible water process, you start heating
temperature under high pressure, because pressure is constant, otherwise it will be steam. What will happen? Directly constant starts coming down. When you start at ambient temperature, it is about 78 already. Okay? If water comes to 200 degree at temperature and pressure, it acts like methanol. What you can do with methanol? Methanol is a solvent, am I right? Why it things? Water at that temperature is very much like what methanol could do, it can do. So sometimes you will see that people are using biodiesel production using subcritical water. Because it becomes green solvent. Go higher temperature, it's as good as acetone, dichloromethane, supercritical, very low dielectric constant, it's very good solvent like hexane. So remember one thing in solvent is okay, so I need to go for a meeting, quick meeting. Okay, so give me 10-minute break and then let's see, next step, right? So, do you know polar and non-polar compounds? Right? Do you know one saying is called light dissolves light? That's how you choose solvents, right? But in non-polar, when you go for non-polar solvents, if you have clean oil, you need some non-polar, right? So light dissolves light. So what water is, you can make non-polar here, and you can make water polar here. Just tune it temperature. You keep talking green chemistry, this is green chemistry. You can use water the way you want to do chemistry. So here biomass is fully soluble. At room temperature input nothing happens. That's some extraction might happen at low temperature, but come here it becomes slightly dissolved, become hexane. In fact, you can do combustion in water. And light a fire in water. Can you think of? You use water to quench the fire, right? But in supercritical water, oxygen solubility is very high. For fire you need oxygen. So you can do that combustion. That's called supercritical water oxidation process. Oxidation is combustion. So supercritical water oxidation is used. That process is used for highly toxic waste. Where you want to get rid of that. You cannot put in landfill. You cannot treat it for it is so toxic and landfill. You do supercritical water oxidation, then literally toxic elimination and all which you will do, and they use supercritical water oxidation. So high end of it. Costly, but it has application for certain things. And supercritical water oxidation is combustion of material. So the product will be CO2 and water will be more. So using water, you can do whole lot of chemistry here. You can tune and become green solvent. So advantage if you are using water, you don't have to dry biomass. Right? You do that. It's not dependent on type of biomass, it's grass, wood, everything can take that. Reduced mass transfer, because water can penetrate very deeply, can be very deep mass transfer regulation in space. I'll show you how you can make solid fuel green coal. Pyrolysis, you do carbonization, right, to make biochar. You can do pyrolysis to make char. in presence of water. You can do liquid biocrude or bio-oil, you can produce in presence of water. You can gasify in supercritical range at higher temperature. You can mix in gas, carbon monoxide, hydrogen and all. So water, what I am saying that it's not always bad. Only thing you have to change the reactor, and reactor becomes high pressure now because vacuum pressure system. You have to pressurize. Okay, and that's the challenge. If you have to have a pressurized reactor, that means you are putting a lot of metals, like thick, big reactor and all. So that's initial capital cost. But we are not dealing with corrosive chemicals, so it's a trade-off. Especially in biomass, if you want to feed at high pressure, I said biomass transportation is a challenge. Pressurized it turns into wet. Water will filter out. Cannot move with water. Right? So you need some screw kind of reactor and other things. So that's a challenge. Salt, which was soluble at room temperature, it will precipitate at high temperature. Escaping and other things. So those are challenges, but it has very good applications. And all technology have applications, but not uniform for everything. Pyrolysis is good for dry feedstock. This one is good for LG. There are a lot of water output waste. So one thing fits all is not the solution. You have to find which one is the best for what. I already talked about this dielectric constant. It goes down in supercritical, and solubility very low, becomes fully miscible. Oil at low temperature, nothing, and then it mixes very well at supercritical range. Diffusivity, viscosity, density all goes down. Diffusivity higher, so it's good for chemical reactions or any kind of reactions. The question comes, we are putting a lot of energy, right? I'm talking 300 to 350 degrees Celsius. So I'll bring you to some fundamental knowledge of thermodynamics again. How many of you know latent heat of vaporization? You have water heating at 100 degrees, it will be water for some time. Then you cross certain limit, then it will start vaporization. That's called latent heat of vaporization. That is required for phase change, liquid to gas. If you are working in subcritical water, supercritical, there is no phase change. Right? That's what we are saying. Pressurized and keep in liquid phase. So that heat of vaporization is safe. So energy by seeing looks like it's higher, but I'll show you the numbers. As an example, if you have a steam instead of subcritical water, its enthalpy is 2.9 megajoule per kg. 1 kg of steam will have energy of 2.9 times that much energy you have to supply to have steam. Alright? But if you want to have not steam but pressurized water at temperature, subcritical water, energy requirement is 1 megajoule per kg, 1/3. So we are thinking energy intensive, it's not energy intensive, it's pressure intensive. You have to have a high pressure system. Okay, energy is not a challenge. All three things you can do. We can make biocrude or bio-oil. I'll show you, we have done a lot. You can do gasification. You can make syngas, methane, you can make it at high temperature in presence of water. You can carbonize and make biochar or hydrochar. Make in hydrothermal, we call it hydrochar. So I go to the application side of hydrothermal where it's better than other technology. It's healthy or high mass content. So some idea about that. How many of you already know or working in microbiology? So what is that microalgae? Grows very fast.
Right? We have right amount of nutrients, light grows. Excess of nutrients implies it grows. In fact, it blooms, I said that one day. And it's uncontrolled bloom, it will cover everything. And we learn to can we control that, then we can grow it. Why to grow it? Because it will clean water. It will pick up nutrients from water. So if we have a wastewater, it will pick up all nutrients from wastewater and it will grow. Why will we grow? One is cleaning, water treatment. Second is it's a biomass. Okay? Biomass without lignin. There is no lignin. Lignin, we were talking about kind of villain in us. Troubles a lot, lignin chemistry and all those things, but they are in fermentation, and this one has no lignin. What it has is lipids, more oil. That's what we are looking for material out of it. What it has is lot of protein. And we need protein, right? By protein diet, we talk protein, animal feed, many other things. And it has carbohydrates. And all these things are easily accessible. It's not hard to say, it's just micron size kind of particle, right? So the change, good point is rapid growth. So if you are looking at photosynthesis efficiency in a very bigger picture, if biomass is better or LG is better, if I got a land and you want to do cultivation, should I go for biomass or LG? Both are biomass at the end, it's kind of, right? Photosynthesis efficiency or growth rate, LG is much better than biomass, right? In 1 year, how much you can harvest this biomass versus LG is much higher than that. So productivity is high. So efficiency, capturing sunlight, efficiency better. Okay? So rapid growth rate. Water. Wastewater can grow, any kind of water can grow into this. Saline water, fresh water, different species, more than maybe 50,000 species are known, even many more than that. But it can grow. It does not require arable land, fertile land. Basically, it's a pond where you can grow. Okay? And the loss is only evaporation loss. Now, it requires CO2 from air, so you can supply through air, but it improves the productivity. You can supply bubble air from two gases. Biological sequestration, carbon sequestration basically, biologically you are sequestered. Direct air capture and biological sequestration going together. Alright? And utilization, CCUS, carbon capture and utilization, you utilize this LG also. Biological capture is not enough at all. You have to do something with that. Here you can utilize. So all those good points coming here, and these are in demand. All three things are in demand. When you analyze LG, you will get these three major components. And if you try growing, cultivating, you can tune these numbers a bit, depending on the species, changing nutrients conditions and all. You can play with that. Lower protein, higher oil. There is a limit to that, but you can tune it. Okay, species dependent, climate dependent, where you are. That's possible. The challenge is there are too many species. Which one to select? Good problem to have, but you have. Cultivation. Now farmers don't know how to cultivate it. So you are looking for a new skill set. We are not talking house or aquarium. We are talking big ponds to maintain. So you need to train people who knows how to grow it. The closest one way will be, you will know a bit, is fishery industry. Right? Fishery industry, aquaculture industry, they know a bit how to maintain nutrients and have fish every fish. So skill set require cultivation. Harvesting. If you take a bottle of LG, how you take LG out of harvesting? How you concentrate? Difficult concentration, 1 milligram per liter, 2 milligram per liter. Not 2 gram per meter. So that's very dilute. Still 1 gram, 2 gram in 1 liter is very less. Then how you process it, downstream processing, and nutrients. Now if we are looking at environmental engineering and environmental science, and nutrients is also very important to watch. It can be pollution. They pick up nutrients for cleaning the water. If you don't do anything with nutrients, it will be released away, right? So nutrients is fertilizer. So you want to grow healthy, then you have to supply fertilizer. Some of the fertilizer was coming from wastewater, some supplement we are giving. But we don't recover the fertilizer or nutrient itself. Oil content is variable. So this is open pond. We used to do in our university. This is from there only this picture. 1 acre open pond we had to attend 5-6 years and then get out. It may look very green, but to harvest you will get 600 milligrams. I said 1 gram at the best, 2 gram in photobioreactor. Open pond is 1 gram per pound. So you are dealing with lot of water. And filtration is not a good choice to take it out. It's too much water, filtration, pressure and chlorine. So how to harvest it? So cooperation, will make up. So that's why I said this fits well for hydrothermal. Let's not remove water to chemistry, presence of water. So there are different energy, protein, carb, and they carry that, and you can choose which one you want. You can cultivate 2 different ways, open pond or photobioreactors. If you go for open pond, the pond which I show outside, it's weather dependent, am I right? Some are winter, rainy, and gets contaminated, so you have a certain control, you will lose some control. It's cheaper to go outside, but contamination is an issue, weather is an issue, right? Closed, go here some design photobioreactors, you can do closed conditions, light control, influence control, everything in control, so you can have a green culture, but you are investing in that, so it becomes very costly. So you have to trade off cost function you want to do. Open pond is scale up easy, you can build big ponds. Photobioreactors, little challenging. Technology is getting available now, so now downstream processing, again, flexibility of the strain is low. If you want to control a strain in open pond, the local strains will take it out, right, over time. In photobioreactor, you can do this. In open pond, we lose water by evaporation. In photobioreactor, so dewatering, even if this is dilute and it's fine, hydrothermal is very less amount. Right? So you want to concentrate it to meet techno-economic. You are not needing just water. So maybe 8-10% you want to concentrate. For that we do centrifugation, flocculation, and all those things. Different motions. Then once you concentrate it 8 to 10%, you can do hydrothermal process, and I showed you the graph, different temperature, different solvent properties, and you can play with those numbers between 200 to 600. You can make whatever you want with all these things. So HTLE has picked up a lot in recently. You are following that hydrothermal liquefaction process is becoming more popular. Especially LG, sewage sludge, food waste, there is a lot of water. Hydrothermal liquefaction is like a simplified version pressure cooking. Little higher pressure than pressure cooker. You can cook everything in a pressure cooking. Heat and temperature you get through like bio oil. This food is better than bio oil. Energy density is here is 32-33 megajoule per kg. You remember pyrolysis oil, energy density was still 60-70 megajoule per kg. Okay? So So this is typically done biofood at 350 degrees Celsius, 320 degrees Celsius in that. In subcritical then you don't go 400 because it does not gasify. So 320, 350, 300 is a good range for making biofood using hydrothermal process. Now if you compare with pyrolysis, that there also you make oil. That oil has a lower density, energy density. Plus pyrolysis temperature is 450, 500. So you cut down 100 degrees. So again trade-off. You are putting high pressure vessel at lower temperature. So economics. So any process development has to be integrated with DEA and LCA. And once you get biofood, I said this is better crude than the pyrolysis oil. It's easier. Again, you need hydrogenation process. You need to add hydrogen, but it gets and you can make it. Reliance has done a lot of work on this. They have pilot plant. They have collaborated a lot with United Airways, National Labs. One time I was working with them long time, so I have good insight of what they are doing. They have big pond. You can go on photobiotic invested at least for last 15 years a lot in this. And over the time, since it is good for wet feedstock, they look at sewage and food waste and many things they are testing in that based on this technology platform, because this food suits them. Get crude, you can go to their refinery. Right? It's better than pyrolysis. So biomass, wet biomass, this is a batch reactor, it can be continuous. Some catalysts if you do is better, you reduce severity of reactions. You get three things, bio oil or biofood. Remember you put water, so water has to come out. When water does not turn in oil, right? So this water is for the phosphate. If it has some dissolved organic carbon, you can treat like a wastewater. A whole lot of nutrients will come here. So you can recycle for pond or you can use for wastewater or many other purposes. This is biofood or bio oil. This is not biochar, it's solid residue, it is hydrochar. Same like biochar, but it has higher hydrogen carbon content than biochar. Because they retain carbon, that's more like coal, green coal. In Europe, some of the countries, heavy industries, they are into green coal using hydrothermal process, hydrochar. Another good point is you can make a lot of carbon material. It's a renewable carbon and it has many different applications. We have been working, my research group working on food waste, LG, and looking at carbon what material we can do. We are looking at electrode material from food waste. Using hydrothermal with carbon, now we need to make it more graphitic, so we are looking at that. I leave it, this one. Case study, you know more than me for India what's going on. Yeah, IT Madras has a lot of work on hydrothermal. IT Kharagpur also doing, IT Delhi collaborated with them, they are doing HDA. This is becoming more popular because of the water thing, a lot of water and better food quality.